So the last generalized linear model that we'll look at is logistic regression. And logistic regression, instead of using the Poisson distribution or the negative binomial distribution, uses just the binomial distribution. And the distribution, this logistic regression is very useful for modeling binary variables, like whether someone is voting Democrat or Republican, whether they have a disease or does not have the disease. So when you want to put like a binary value of 1 or 0 on the y-axis, logistic regression is incredibly useful. So actually, we're here going to simulate a machine learning classification problem. So imagine that you have blue dots and orange dots. So the blue dots might be has cancer, and orange dots doesn't have cancer, or blue dots are vote Republican and orange dots doesn't vote Republican. And we have a simulated data set that looks like this. This is a simulated data set in 2 dimensions, where we we have the orange dots, right? So you have cancer, don't have cancer, you're voting Republican, not voting Republican. The orange dots are up top. The blue dots are on bottom. And the orange dots and the blue dots have values that go between, in this case, -1 and 3. Right? And so we want a simple linear, we're going to use this as an example for our logistic regression data. So we could simply make this, we could fit this with a simple linear model. So in the simple linear model, we call the orange dots 1, and we call the blue dots 0. And then we just set y equals mx plus b, and we fit it as we normally would. And so this is okay. Maybe we get this line here, right? So this we can sort of think of this as like the probability that you have cancer or don't have cancer as a function of whatever the input data are, right? And you get this line, and this line is fine. But like the examples that we saw for the roadkill, one of the problems with this line is that it can go greater than 1 or less than 0, which doesn't necessarily make a lot of sense, right? If you only have the 2 categories, what does it mean to have a value of 1.5 or 2 when in fact the category of being having cancer or not having cancer is only assigned to 0 or 1. So instead of doing this, we can, as an alternative model, fit a logistic regression. So we do that in R. We go back to the GLM library that we used for the Poisson distribution, but now we just type in binomial instead of Poisson, and we get this fit that's here. And we can look at the breakdown of the binomial distribution. So we assume that our y data is binomial distributed. We say that the expected value is just pi, right? The probability of getting ahead. So that's going to vary from 0 to 1. The variance we will recognize is n times p times 1 minus p. So we've been drilling that as the variance of the binomial distribution since the very first lectures in the class. And then this has a sort of a special linker function. It's not as simple exponential as we saw for the Poisson and negative binomial distribution, because the binomial distribution, this value can only be between 0 and 1. Right? So we have to find a way to write to constrain this value so that it's between 0 and 1 as a function of our input parameters. And so the logistic regression uses this logit function, after which the logistic regression is named for. And so it puts our values here. So in this case, again, if we only have 1 parameter, we have an intercept term and then beta times our parameter. And you can work it out, right, that this value can only be between 0 and 1, right? So you can have this go towards 0, in which case the whole value goes towards 0, or you can have this thing approach infinity, in which case you have infinity over infinity, which goes to 1. So this only is defined between 0 and 1. And so the logit function, of course, you can read more about it on the wiki page, and with much more math than we're doing here. So again, this has a likelihood function. We'll let smart people tell us what that likelihood function is. We'll let smart people tell us how to maximize that likelihood function, and we're good to go. I say that, but of course we recognize here, right, some of the parameters that this is not looking unfamiliar, unrelated to, of course, the likelihood of the binomial distribution. So using our simulated data set, so again, right, this is people who have cancer, people who don't have cancer, the expression of one gene, right? And we can run these simulated data sets 3 different times. And we can see that sometimes the linear regression and the logistic regression are very, very close, agree very closely. Sometimes they disagree, right? But the logistic regression kind of gives us a more natural saturating function. And again, the biggest difference really between them is that the logistic regression never gets a value greater than 1 and never gets a value less than 0. So you'll see the logistic regression all the time, modeled for binary variables. It's one of the most popular and commonly used regression techniques.